500 million wheel rims are consumed globally every single year. They roll the equivalent of billions of miles, supporting the weight of the entire mobile industry. At first glance, they look like simple circles, but in reality, they carry vehicles across every kind of terrain. But this is just the beginning. Why is the process so rigorous? It seems the shape alone suffices. To meet massive demand, however, rims are engineered from refined alloy and pass through high-pressure casting. One can notice how equipment precision machines the raw forms. This creates a durable metal structure capable of bearing continuous load without deformation. Rigorous quality inspection verifies every unit. It gets more complex further on. The camera glides over the sleek surfaces. This keeps every vehicle stable. It is the intersection point of speed, weight, and mechanical engineering. The component is ready for the road. Just a few meters beneath the surface of the vast red-tinted earth lies the bauxite layer, waiting to be transformed. Why is the depth of these deposits so critical for the mining strategy? It might seem that such valuable ore would always require deep underground shafts to access. But because bauxite lies so shallow, geological teams extract it through open pit mining in thoroughly surveyed zones. High-capacity excavators strip away the topsoil, which is piled and preserved to restore the land once the operation concludes. Beneath this layer, the soft rock appears in rich shades of pink, brown, or deep red, holding a high concentration of aluminum oxide. But this is just the beginning. Trucks transport the mined raw material from the open pits to the processing plant for immediate treatment. Because the chemical reaction requires maximum contact area, the first stage involves crushing the ore into smaller pieces using large industrial crushers. The finely ground bauxite is then fed into reaction tanks, where it mixes with a caustic soda solution under high temperature and pressure. Under these extreme conditions, the aluminum oxide dissolves completely to form sodium aluminate. One can notice how insoluble impurities are filtered out as red mud, while the remaining solution is gradually cooled. This drop in temperature allows pure alumina crystals to precipitate, creating the feedstock for the next phase. Transition to the next level. At first glance, the white alumina powder looks chemically simple, but in reality, transforming it requires an intense electrolytic reduction process. The purified material is transferred into cells containing a molten electrolyte bath maintained at nearly 1,800 degrees Fahrenheit. A powerful direct current is applied, forcing the aluminum to break free from its chemical bonds. While oxygen escapes upward as a gas, the aluminum settles at the bottom of the cell as a flowing liquid metal. This process runs continuously under strict control of electrical intensity and material purity. It gets more complex further on. The camera glides along the line as the pure, bright silver metal emerges, possessing exceptional workability. Massive, heat-resistant ladles transfer the molten aluminum from the electrolytic cells to the casting area. During this stage, the temperature is strictly maintained at roughly 1,292 degrees Fahrenheit to ensure the flow remains liquid. The metal pours down an angled trough or directly into molds made from heat-resistant steel or cast iron. Depending on the order, the facility produces standard ingots weighing between 48 and 55 pounds, or long billets that weigh several tons. It is visible how the consistent stream of metal fills the forms without turbulence. Everything only gets more complicated. Therefore, heavy airflow units and water cooling circuits are positioned around the molds to help the metal solidify quickly yet evenly. This controlled cooling reduces internal stress and prevents cracks from forming in the structure. As the metal cools, a thin gray film naturally forms across the surface due to contact with the oxygen in the air. Once solidified, each ingot or billet is removed and rigorously inspected for weight, surface finish, and dimensional accuracy. The material is now ready to move forward for rolling, extrusion, or final manufacturing. Three-dimensional design software dictates the fate of every aluminum block long before it touches a mold. The material is packaged or moved forward for rolling, extrusion, or end product manufacturing. But its true journey begins with technical drawings. These blueprints determine the geometry, structure, and performance requirements the wheel must ultimately fulfill. Every wheel rim is designed through a delicate balance of aesthetics and performance. Engineers carefully determine the number of spokes, depth profile, load-bearing surfaces, optimal weight, and thermal dissipation capability. Why is such extensive digital structural analysis required before production? It might seem sufficient to cast the metal into a standard shape immediately, but without these simulations, the model would fail to meet the rigorous demands of real-world conditions. One can notice how the virtual model highlights stress points during multiple cycles of testing. The design must be strong under load, light enough to reduce fuel consumption, and durable enough to survive harsh environments. Only after the design meets all specifications is its data transferred into the manufacturing line. From that moment, the once formless aluminum begins to take on a defined destiny. It prepares to enter forging or casting, eventually becoming the spinning backbone beneath every vehicle. Once the design is complete, the metal moves into the mold where it is forced into shape for the first time. Rectangular aluminum billets are cut to standard length and delivered to specialized casting facilities. There, they are remelted inside controlled furnaces. The temperature is held steadily between 1,300 and 1,400 degrees Fahrenheit. This thermal consistency ensures proper fluidity and metal cleanliness before entering the mold. The molten aluminum is then fed into a sealed die using low or medium pressure casting systems. Under continuous force, the metal fills every corner of the cavity with high accuracy, forming the basic shape of the wheel rim within seconds. It gets more complex further on. The die itself is made from heat-resistant alloy steel and engineered with extremely tight tolerances. This ensures that spokes, reinforcing ribs, and bolt holes are reproduced exactly as designed. Once solidified, the rim is removed, rapidly cooled, and passed through a sequence of follow-up treatments. These include flash trimming, geometric inspection, ultrasonic flaw detection, and preparation for machining. And this is not the limit. From a reservoir of molten metal, the first true form of the wheel rim emerges accurate and balanced. However, alongside casting methods, many high-end wheel models are produced through forging. Here, the process differs. Metal is not poured into a mold, but compressed under immense mechanical force. The aluminum stock comes as a solid cylindrical billet, cut to standard length. At first glance, the heating process looks similar, but in reality, the aluminum never reaches a liquid state. It is heated until it reaches a plastic, workable state, and when the required temperature is reached, each billet is placed onto a die. It is subjected to the force of a massive hydraulic press, often between 6,000 and 10,000 tons. Under this pressure, the internal grain structure of the metal is compacted and realigned along the direction of force. This action eliminates gas pockets, micro cracks, and the defects commonly found in cast material. The result is a forged wheel blank, with mechanical strength increased by as much as 30 to 40% compared to a cast wheel, while also being noticeably lighter. Forging allows material reduction in non-load-bearing zones while maintaining rigidity in critical areas, creating a structure optimized for both performance and durability. Significant amounts of heat remain in the structure of the wheel blanks immediately after deformation or pressure casting. To prevent warping and maintain dimensional stability, the automated line transfers each blank into a water cooling system. Why is this rapid temperature drop so strictly controlled? The metal has already taken its shape and appears solid. But without this cooling phase, the internal stresses would distort the geometry, rendering the subsequent high-precision machining impossible. Inside the quench tank, circulating water rapidly draws heat away from the alloy to bring it down to a controlled level. Simultaneously, the fluid washes off oxide dust and residual metal particles from the surface. One can notice how automated inspection systems using cameras or thermal sensors monitor the blank. At first glance, this is a short stage in the line, but in reality, the precision of the entire manufacturing process depends on the stability set here. 6,000 to 12,000 revolutions per minute is the speed at which cutting tools spin inside the enclosed machining cell. The basic profile of a wheel rim is only the beginning of the transformation. Modern computer numerical control systems operate on 5 axes to carve directly into the preformed aluminum alloy. This technology allows the mechanism to machine the wheel from multiple directions without repeated repositioning. But this is just the beginning. Mechanical accuracy remains absolute throughout the entire process to ensure the wheel meets safety standards. Complex spoke geometry and bolt holes demand strict adherence to positional precision. Tolerances are often kept below 0.02 millimeters, which is finer than a human hair. Every surface undergoes refinement to reach its intended contour. In large-scale facilities, robots handle billet loading, tool changes, and product removal to ensure consistent output. A complete wheel can be machined in under 30 minutes, even for intricate designs. As a result, modern factories produce hundreds of rims per day while maintaining perfect uniformity across every batch. The process is only gaining momentum. Before undergoing surface treatment, each wheel rim requires thorough pre-cleaning to remove debris. Robotic arms equipped with industrial wipes and compressed air nozzles move around the rim automatically. It is visible how they sweep the surface with precision to remove remaining chips and cutting oil left over from machining. The nozzles focus especially on spoke channels and bolt holes, where metal residue often accumulates. For more complex areas or critical inspection points, workers still step in with cloth and inspection lights. They wipe the surface by hand to ensure no detail is missed by the automation. This stage serves more than just cleanliness. It prepares the rim for the next operation to be executed with maximum accuracy. Transition to the next level. Even when the surface has been machined to near perfection, appearance alone can never guarantee the integrity within. Rigorous evaluation begins with pressure testing and liquid penetrant inspection. Inside a pressurized water tank, air is pumped into the cavity of the rim to detect leaks. If any crack or void exists, even one as small as a pinpoint, air will escape and rise as faint trails of bubbles on the surface. Fluorescent penetrant testing takes this analysis further in some advanced factories. A special luminescent solution is applied to the rim before exposure to ultraviolet light. The glow reveals microfractures buried deep inside the alloy structure that are invisible to the naked eye. Only the wheels that pass this demanding inspection are permitted to continue into surface finishing. The component is now ready to move to the next processing phase without haste. 100% of the wheels entering the surface finishing zone must first pass a demanding structural and leak tightness inspection. Only those that survive this rigorous check are permitted to proceed to the powder coating booth, the first stage of the process. Here, automated spray guns align to apply a black base layer using precise electrostatic coating technology. Why is the paint powder charged with a polarity opposite to that of the aluminum rim? At first glance, a simple spray seems sufficient to color the metal, but in reality, this electromagnetic difference ensures the particles cling uniformly to every contour without requiring a single drop of adhesive or bonding agents. One can notice how the fine powder coats every surface, from the face and spokes to the inner barrel. The result is a smooth, ultrafine layer, measuring only a few microns thick. This foundation resists corrosion and shields against weathering, while providing the ideal base for subsequent finishes. Consistent tone depends on this bond, but this is just the beginning. 375 degrees Fahrenheit is the temperature inside the curing oven, where the powder melts, levels out, and bonds permanently to the metal. This sets the groundwork for durability. It gets more complex further on. The wheel advances to the most visually defining stage inside a sealed spray booth. Robotic arms apply multiple layers of fine paint, following pre-programmed paths with precision down to every edge and recess. Whether for deep gloss black, metallic silver, or graded shades of gray, each paint type is pre-mixed to a specific formulation to ensure consistent coverage. The robots move in coordinated arcs while pressure, flow rate, and spray distance remain under tight control. It is visible how the paint sits thin and even across curved surfaces and sharp spoke transitions. More than aesthetics, this coating forms a barrier against ultraviolet exposure and road salt. Once the final layer is applied, the wheel returns to a curing oven to lock in color and stability. Thus, the product achieves the durability needed to meet global quality standards. Three key factors, color, stability, and durability, are locked in by the oven to meet global quality standards. Once the paint has fully cured, the wheel enters final inspection, a stage where even the smallest deviation can determine whether it is accepted or rejected. The process allows no room for error. This rigorous sorting defines the reliability of the final product. Why is each rim mounted onto a dynamic balancing machine? To the naked eye, the structure looks solid, but spinning it at high speed allows engineers to measure concentricity and weight distribution. Any imbalance beyond the allowed tolerance is flagged immediately. The machine marks the unit for correction or removes it from the production line entirely. At first glance, the parallel visual inspection seems redundant, but in reality, it catches what machines might miss. One can notice how automated sensors and skilled technicians perform a detailed check. They evaluate paint finish, rim edges, and every spoke surface to ensure no scratches, peeling, or cosmetic defects have formed. It gets more complex further on. All gathered criteria are compared relentlessly with the original design specifications and the manufacturer's quality standards. Only after passing every benchmark is the wheel cleared for packaging. It is visible how each unit is wrapped with scratch-resistant film and secured with cushioning inserts. The rim is placed into a dedicated carton with traceable barcode identification, ready to begin its journey across the world. Dozens of strictly controlled manufacturing stages separate the raw aluminum ingot from the finished wheel rim. The creation of a component is the result of heat, pressure, and precision. From raw metal to the final form, the material changes completely. But this is just the beginning. The work does not stop here. Why is every detail, from geometry to weight, checked? It seems simple to cast a basic shape. However, this scrutiny reflects the level of technology and craftsmanship behind the production line. At first glance, the wheel is just metal, but in reality, even the paint finish is a technical feat. One can notice the smooth surface. The wheel is now prepared to begin its journey across the world.